don't know of any new announcements. The meetings, informational meetings or sessions on the summer Pell Grant, those were yesterday. If you didn't get to go to them, go by Financial Services and find out. And then the rest of it's about tutoring, and you know about that. Please, I encourage you, volunteer to tutor. Well, you're not volunteering. They actually pay you to tutor, but volunteer to be paid to tutor, and go with that. All right. I didn't mark the roll. It's going to take a while because so many people are here. Daniel's here, and Sarah's here. Wow. I had to get that over with. Okay. Hopefully the others will be coming in. All right. Any questions on what we've done up till now? All right. Here was example 1. We got right up to it, but didn't get to do it. So, this is your issue. 2 cosine x plus sine 2x equals 0. How in the world can we solve that equation? I see 2 problems with it. Do you see any problems with it? You got 2 different trig functions, so you can't just solve for one. And what's more, one of those trig functions is to 2x, the other is only to x. So you can't use Pythagorean theorem or Pythagorean identity to help you there. So what are we going to do? It's not as dire as it seems. What's the latest identity we ran into? The double angle formula. Remember how that goes? So let's leave the 2. Oh, let me get my pen activated. Okay. Let's leave the 2 cosine x alone for now. Plus, but instead of sine 2x, what is sine 2x? You got it. 2 sine x cosine x. And that now is equal to 0. All right. Your prospects look any better? You still got 2 different trig functions, but what can you do to this one that you couldn't do to the other one? Say again? I don't think so, because they're not like terms. This is something that's going to split them apart, kind of. What's the F word? Factor! Can we factor anything there? Not just cosine. How about 2? Let's factor out a 2 cosine x. And what do we have left in the first term? 1 plus sine x. That's looking better to me, isn't it to you? And that product is equal to 0. Now, if anytime we have a product of 2 entities, or 2 or more entities equals 0, what does that tell you? The only way you have 2 entities multiplied together to give you 0 as the answer, one of them's got to be 0. So let's just set them whichever way you want them. What would that be? Either 2 cosine x equals 0, or 1 plus sine x equals 0. Okay? Now, any problem with the 2 there? Is what? You can divide it out if you want to. Or you could say 2 is either 2 equals 0, cosine x equals 0. 2 is never equal to 0. So because that's an equation, you can divide it out. Okay? And with absolutely no problem, that gives you cosine x equals 0. Now they didn't give us a limit here, so we're going to have a general solution. What are the values of x for which cosine x is equal to 0? All your half pi's. So you can write this as x equal, let's call it n pi over 2. That will cover them all, right? when n equals 0. Wait. Oh, that's the problem, isn't it? No. Yeah, that won't. Huh. Okay. Better way. That won't quite work because n equals 0 gives you something wrong. Do it this way. Pi halves plus n pi. How about that? That'll give you every half pi out there. When n equals 0, it's pi halves. When n equals 1, it's 3 halves pi. When n equals negative 1, it's negative half pi. That covers them all. Now, most of the time with cosine, we say 2n pi. Why do we say n pi now? Because every period has 2 zeros exactly midway between. So it'll have one at pi halves and then another one at 3 halves pi, but they're exactly n pi apart. Yeah. So that works for that one. Okay, how about the other side? Other equation. What would you do here? Subtract 1 from both sides of the equation. That sounds like a winner to me. And what that gives you? Sine x is equal to negative 1. And when is that true? Three halves pi. Plus, now this time it'll be 2n pi, right? Because that only happens once a term. But guess what? These are your half pi's that are covered here too. That's only every other one of them. This is every one of them. So you really don't need this. This covers them all. Covers them all. Okay? And what they do, they list them both. Okay? But, you know, there's no reason to. That covers every one of them. Okay? Now, like every other example in the book, there's a checkpoint here. Then that provides an audio-video solution, has an audio-video solution at larsonprecalculus.com. So do your checkpoints as soon as you can after class, and if you have trouble with them, go to larsonprecalculus.com. All right, we did it. Let's see what they did, and I bet you they list them twice, don't they? Not all of them twice, but some of them. So let's see what they do. First thing they do, begin by rewriting the equation so that involves functions of x rather than 2x. But they didn't do that yet. They just rewrote the equation first. Oh, that's a useful step. Okay? And then they do, exactly like you said, expand the sine 2x to 2 sine x cosine x. Right? So now we have that in our equation. Even though it's a little bigger and more awkward looking, it's actually easier to deal with because you don't have any double angles in it. Okay? But, and it also allows you something to factor out. So you factor out a 2 cosine x, leaving you 1 plus sine x equal to 0. Square each of those two be equal to 0. Now, I don't like the fact they say and in there. It really should be or. So either 2 cosine x is equal to 0 or 1 plus sine x equals 0. One or the other. You don't have to have both of them. One or the other. Okay? And then the first one, that's pi halves and 3 halves pi in the first one cycle. And the other one gives you 3 halves pi, which duplicates the first one. And then when you add 2n pi to this one, and, oh, I see what they did. I'm sorry, I misread what they wrote. They wrote both of these. This will be pi halves plus 2n pi. That would be either one of these is 3 halves pi plus 2n pi. But guess what? You could have made it much simpler by just writing that. Okay? Because if you take out this, you cover those. So, for n is any integer. It said try verifying them graphically. And when you do that, you'll see you get them every n pi, and you can leave off every half pi, basically. Okay. Not just the small half pies and the big half pies, it's all the half pies. Okay. I think we're ready for example 2, unless there's any questions on that. Are there? Okay. Now they're jumping right to power reducing formulas without doing example 3. So let's, 2 or 3. So let's do example 2. They seem like they do the easy ones and skip the ones that are a little more involved. All right. Now, sorry. My head is clogging up on me. Evaluating functions involving double angles. Okay? Use the conditions below to find sine of 2 theta, cosine 2 theta, and tangent 2 theta. So what we know here, that's what we're looking for. We're looking for sine 2 theta, cosine 2 theta, and tangent 2 theta. Okay? Given that cosine theta is equal to 5/13, seems like we've seen something like this before, and that 3 halves pi is less than theta is less than 2 pi. Okay. So where are we, Waldo? Where does this put us? You're not in the first quadrant. That's 0 to pi halves. You're not in the second quadrant. That's pi halves to pi. You're not in the third quadrant. That's pi to 3 halves pi. You're in the fourth quadrant. That's between 3 halves pi and pi. The 2 pi, right? So that's where we are. Now, first thing I ask myself, being the cynic I am, could cosine theta in that quadrant ever be positive? Yes, of course it is, because all students take calculus. The cosine is positive there. Okay? So yes, this makes sense. Okay? Now, from there, we have to calculate sine of 2 theta, cosine 2 theta, and tangent of 2 theta. Okay. Sorry, I am running out of energy. It happens every Thursday. And the strongest thing was, I was telling my wife last night, when I was at home on the farm, I was working like a dog, you know. I mean, I was cleaning porches, scrubbing, things, mildew and pollen, and mowing the grass and doing all sorts of things. And I never felt this. I mean, I get tired, of course, but I just didn't feel completely worthless in the middle of the day. And driving in this morning, I was pondering that. Why am I feeling so tired? Well, then when I did go to bed, I slept. I slept as late as I wanted to sleep. Okay? Now I'm getting up at 5:15. That may be the issue here. So I think I was allowing myself more time to replenish. And I'm not allowing that now. And man, this is just driving me nuts. Okay. All right. Now, we need to find sine of 2 theta. So the first thing I would do, or what would be the first thing you would do? Sine of 2 theta. Wouldn't you figure out what that is anyway? And what is that? Especially since we just did it last example. What is sine of 2 theta? What is sine of 2 theta? Huh? 2 sine theta cosine theta. All right. Sydney's here. Were you stuck on the interstate? Yeah.
It only takes me like 30 minutes to get here. It took me an hour.
What's that?
It only takes me 30 minutes to get here. It took me an hour.
Yeah.
It's crazy.
Yeah. My wife saw that there was a problem, and she said, "Don't go that way."
Yeah.
But then going through UAB, everybody else was trying to avoid the interstate, so all the surface roads were clogged too. But it wasn't as bad as the interstate. So I was about 15 minutes late getting here. Yeah. All right. So we're doing example 2 at the top of page 382. All right. We just had determined that the sine of 2 theta, that's what we're looking for, sine of 2 theta, when cosine theta is equal to 5/13. But theta is in the fourth quadrant. So here we have sine 2 theta, we just determined to be 2 times the sine theta times the cosine theta. Well, we're part of the way there, because we know what 2 is. It's 2, okay? We know what cosine theta is. They gave it to us. But what we don't know is what sine of theta is. Remembering theta is over there in the fourth quadrant. I do know what the sine of theta is. In other words, the SIGN sine of the SIN sine of theta. What is it? Negative, exactly. Sine is negative in the fourth quadrant. So our whole product here is going to be negative. You know it's got to be. 2 is positive, cosine's positive, but sine's negative, so that's the result's going to be negative. But we've got to come up with a value for it. Okay? So what I'm going to do is draw me a circle. Anyone want to make a guess of what circle that will be? Hint, it's not a unit circle. It's not going to be a 13 circle. Okay, we love those, don't we? So what I do for these, I go halfway. This is 13 out here. Okay, so I go almost halfway and make that 6 and just past it is 7. And then halfway between 0 and 6 is 3. And then I split those up into 1 and 2 and 4 and 5. Okay, and halfway between 7 and 13, I believe, is 10. And then I split this up into 8 and 9 and 11 and 12. Okay? It's kind of awkward, but it's doable. Okay? So if this is a 13 up here, then almost halfway is going to be a 6 and then a 7. And then halfway is going to be a 3. And then I'll split it up into a 1 and a 2 and a 4 and a 5. And halfway here is going to be a 10. And then that'll be a 8 and a 9 and 11 and a 12. Okay? Do the same thing out here. This is a minus 13. So almost halfway there will be a minus 6 and a minus 7. And halfway between there would be a minus 3. I'll split it up and do a 1 and a 2, minus 1 and minus 2, and a minus 4 and a minus 5. This will be your minus 10 again. And that will be 8 and a 9. Negative 8 and negative 9, and minus 11 and minus 12. Same thing here. This is a minus 13 down here. So almost halfway there will be a minus 6 and a minus 7. And halfway there would be a minus 3. And that will be a minus 1 and minus 2, a minus 4 and a minus 5. Halfway here would be a minus 10. And that will be a minus 8 and a minus 9. And a minus 11 and minus 12. They get worse as I go on. Okay. All right. There's a good old 13 circle. Okay. Now we're in the fourth quadrant. And the cosine, what is cosine, by the way? Adjacent over hypotenuse. So what's your adjacent axis here? That's the x-axis. So that's going to be your 5. So we'll be positive 5 on the x-axis. That would be right here. And then we'll be on the circumference, so that's where it's going to be. So this is approximately somewhere there. That's our angle theta. Right? Well, what is the sine of that angle theta? Now, don't look at my circle, because my circle may be off a little bit, but how can we do that? If we know the x here is 5, and our r is equal to 13, how do we get our y? Say again? Yes, the Pythagorean theorem. It would be 5 squared plus y squared is equal to 13 squared. Very good, right? What's 5 squared? 25 plus y squared is equal to, anyone know what 13 squared is? I believe it's 169, but someone check me on that. I believe that's right. Yeah, okay. Now, what do we do next? Subtract 25 from both sides. And what does that give you? This goes to 0. Y squared is equal to 144. Anyone want to make a guess of what y is? Where are we? Negative 12, exactly. You decide the plus or minus on where you are. That's a negative 12. And look at that. My picture almost looks right, doesn't it? Look at that. Amazing. So my y is negative 12. What does that help us with? That's what your sine theta is. It'll be 2 times, and what's sine theta? Negative 12 over 13, exactly, times cosine theta, which is 5/13. Okay? And this will be, I'm going to do it this way, 2 times 5 is 10, times the negative 12 will be a minus 120, right? Over, and we already know what 13 times 13 is, right? 169. Perfect. There's sine of 2 theta. Without getting a protractor down and trying to measure it. Okay. We got it. Okay? And it's a negative. Okay? Which kind of makes sense, because if you double this angle here, that's going to double basically 270. So you're going from here to that would be 90, 180, 270. Then plus a little bit. Yeah, you're going to be in the third quadrant. Sine negative there. All right, that's looking good. All right, how about cosine 2 theta? Can we do that? What in the world is cosine 2 theta? Anyone give me a hint? Oh, it's been a long time since Tuesday. What was cosine 2 theta? What was cosine 2 theta? Nope. You can write it several ways. Squared theta minus sine squared theta. Now, the only disadvantage to that form is I'd have to trust that I got this one right. And, of course, I feel good about it. But there's another form, 2 more forms for cosine 2 theta. Can someone give me one of them? 2 cosine squared theta. Second? Minus 1. You know, I kind of like that one better, because that only uses what I know is true, not what I think is true. Okay? So let's go with that one. Okay? And that will be cosine 2 theta. I'm going to put equal rather than a comma. 2. And what's cosine theta? 5/13. But we're going to have to square that. Minus 1. Okay? So what is 5/13 squared? 2 times 25 over 169. Okay? Minus, and since my denominator there is a 169, I want to write my 1 as how many 169ths? 169 169ths, right? Okay? Well, 2 times 25 would be 50 169ths minus 169 169ths. That looks like that's going to be 119. Negative 119 over 169. Right? By that? Okay. So guess what? This is awful close to your diagonal there. It's not quite, because your sine is negative 120 over 169, and your cosine is negative 119 over 169. Can't get much closer than that to being exactly on the diagonal there, but you're awfully close. Okay. Now, they also ask for tangents. So if we gotta go through and do that old formula, that's, if I'm remembering right, it's tangent, 2 tangent theta over 1 minus tangent squared theta. Oh man, then we have to figure out what tangent theta is from all this. Or what also is tangent 2 theta? Isn't it? Sine 2 theta over cosine 2 theta? Oh yes! And that I think will be much easier to do, won't it? And I'm lazy. I like to find the easy way. Tangent 2 theta is sine 2 theta over cosine 2 theta. And what was my sine 2 theta? Negative 120 over 169 over the cosine 2 theta, which was negative 119 over 169. And the 169s go out. The minus signs go out, and what are you left with? 120 over 119, which is awful close to 1, okay? Not quite, awfully close. You're right at that diagonal. Not quite there. And does that make sense? We said we're somewhere here in the third quadrant, we feel like, and this puts us almost right in the middle of the third quadrant, where the cosine is also negative, but tangent 2 theta would be. All students? Okay. Yes, it's positive. So sure enough, even that works out nicely for us. Okay. Now that's writing all over the board with it, but if you're okay with that, then yeah, and they did it, I think, just the same way we did. So let's clear it and watch them do it then. All right, to clear it? Okay. What will they do first? Oh, no, this was the end. Oh, that's right. They don't have this one. Sorry. Duh. Okay. In the book, you see they have negative 1/20th over 169, negative 119 over 169, and 120 over 119. And they also have a checkpoint that you can find sine 2 theta, cosine 2 theta, and tangent 2 theta for a different angle. And sine theta is equal to 5/3, and you're in the first quadrant. Should be fairly straightforward. I think a little bit easier than the one we just did, because you're in the first quadrant. All right, let's do example 3. Uh-oh. They're not satisfied with double angle formulas. They want us to derive a triple angle formula, but at least just one of them. So let's try that. Let's rewrite the sine of 3 theta. Oh, I'm sorry. They've gone back to x's, which is fine. It's a little easier to write than a theta. Sine of 3x in terms of, which in math we sometimes say ITO, in terms of sine theta. Or x, sorry. Once I get on to thetas, I can't let them go. Okay. How are we going to do that? It's another way to write 3x as a sum.
2x plus x.
Say again?
2x plus x.
Yes, 2x plus x. Let's try that. Let's do the sine of 2x plus x. That's 3x, isn't it? So we're doing the same problem, right? But now we have a sum formula. Do we remember what that one is? Sine of 2x cosine 2x, x, sorry. Getting carried away with my 2's there, okay. Cosine x plus cosine 2x sine x. Perfect. Oh, but we still got two x's in there. What can we do with those? Say again? Okay, use the double angle formula. What's sine of 2x? 2 times the sine of x times cosine x times another cosine x, so that will be a cosine squared x, won't it? Nice. Okay, plus, what's cosine 2x? Been a long time. What's that? Oh, which one? Let's do the one with only signs, okay? Because we're trying to get it in terms of signs, aren't we? Okay, let's try that. Okay, let me, whoops. Okay, yeah. 1 minus, what do you say? Okay, I cannot. 2 sine squared x. Is that right, what you said? Okay, and that's times the sine x. Yeah, get out of there. Okay. Now, 2 times the sine x, but it says in terms of sine x. And there we have a cosine squared x. Can you write cosine squared x in terms of sine x? Especially since it's squared. Yes, that's 1 minus sine squared x, isn't it? So we'll write that as 1 minus sine squared x. Right? Plus, and let's multiply through, that would be a sine x minus 2 sine cubed x, right? Because you got, do this here, 1 times sine x is sine x, minus 2 sine squared x times sine x will be a minus 2 sine cubed x, right? Let's do the same thing here. What does that give us? 2 sine x, the writing takes a while, minus 2 sine cubed x, right? Plus sine x minus 2 sine cubed x. All right, let's combine like terms. What do we have? 3 sine x minus 4 sine cubed x. My goodness, there we've done it, okay? We have written sine cubed x in sine of 3x in terms of sine x alone. And that's exactly what the book got to. Good for them. And guess what the checkpoint is? Do the same thing for cosine 3x, only do it in terms of cosine x. It won't be the same, but it will be some combination. Okay. Any questions on that? All right. Sorry. My throat is so dry. Now we're moving to the power reducing formulas. Okay. Now, just a little bit of note here. Notice what happened when you had a double angle formula. It was a sine or a cosine or a tangent of a double angle. But then what did you wind up with? You wound up with something of a sine times a cosine, which basically is a second power, or you had a cosine squared minus sine squared, which is second powers, or 1 minus 2 cosine. You always had second powers. And tangent went from being a tangent of 2x or theta or whatever to tangent squared over 1 minus tangent squared. No, tangent. Yeah. No, 2 tangent x over tangent squared x. So again, you wound up with, well, if you went from a single power to a squared power, maybe if you went the other way, kinda, you might have to do some manipulation here. You could go from a square to a single power. But you might have to introduce some double angles. And that's exactly what these formulas are going to do for you. If you don't like squaring, then go backwards. Now they just give them to you here, and I really don't like that at all. Okay? So I want to show you how you got these. Okay? And it's from 2 of our favorite identities that we already know. Okay? One of these is the cosine double angle formula. Let's start with that one. What is cosine to u? Remind me. Cosine squared u minus sine squared u. Now, I think I pointed out to you before, what does that look at? Awful close to, but not the same, Pythagorean theorem, which was, okay, I'm going to start with the 1 on this side is equal to cosine squared u plus sine squared u. Yes. Don't they look somewhat similar, but not the same? Okay, now the first thing I'm going to do is just sitting over here begging to be added together. Let's do it. Let's add this equation to that equation. And what does that give us? Cosine 2u plus 1 is equal to 2 cosine squared u plus 0. Right? Now let's divide both sides of this by a 2, if I can get it to right, okay? And that gives us that cosine squared u, a square term, is equal to, and they reverse the order and say 1 plus cosine 2u over 2. And that's exactly what they get here. Look at that. That's what cosine squared u, a reversing. But what you lose a power, but you gain a double angle. Well, before we were losing a double angle, but gaining a power. So yeah, this is what it makes sense. Okay, so that's how we got that one. So I don't have to sit down and memorize it. I can just always derive it, because I hate memorizing. Okay? It's not one of my favorite things. Okay, now we're going to start with the same 2 identities that we had before. If I can get this to erase. Okay. But this time, I want to eliminate my cosine squared. How can I do that? Actually, I want to change something. I mean, not change it. I want to write it differently. I want to write this one on the bottom. Cosine 2u is equal to cosine squared u minus sine squared u. Okay? And take it off the top. Okay? Because it's easier, to me it's a little easier to see this way. Okay? And that also will explain why they reversed the 1 plus that we had before. We came up with cosine plus 1, which is the same as 1 plus cosine. Okay, this time we're trying to eliminate the the cosines. So what we're going to do, we're going to subtract, right? And what will that give us? 1 minus cosine 2u is equal to, when you subtract, they go away, right? And what do you have here? 2 sine squared u. And since I don't want 2 sine squared u, I just want 1, we'll divide both sides by 2. If my writing would work, okay, the 2's go out, and there we have sine squared u is equal to 1 minus cosine 2u over 2. Alright, so there we get that one. Alright, now do we have to get that really sort of messy double tangent formula and try to work with that? No. All we do is for tangent squared u is to do sine squared u over cosine squared u, right? That's tangent squared u. And that will give you this over that, which of course the 2's can go away, and that gives you 1 minus cosine 2u over 1 plus cosine 2u. There you go. Now notice, you're going from a square to a single power. Everything was cosines here, but both of these others are only cosines here. So these power reducing formulas only get you down to cosines. It's not really an easy way to get you down to sines or tangent. But it gets you down, reduces the power from a square to a single, but they're always in terms of cosine of a double angle. R2. Okay. So that's how we get those. The other thing that's making this morning a little worse is quite often after my first class, I'm already getting a little tired. I run down and get a swig of Dr. Pepper. I didn't have time today, so I'm going with no caffeine, so forgive me. Okay. So let's move on to example 4, and let's see if we can do it. Uh-oh! Why did they do this to us? They jumped it all the way up to a sine 4th x. It says rewrite sine 4th x in terms of first powers of cosines of multiple angles. How in the world are we going to do that? What you reckon sine 4th x is anyway? It's sine squared x squared, exactly, or multiplied by itself. Whichever way you want to do it is fine, okay? So let's just deal with sine squared x. What is it in terms of cosines of multiple angles? What was sine squared x? It was a long time ago, but we just did it, didn't we? 1 minus cosine 2x over 2. Wasn't it? And then we're going to square that. Well, I'll do the denominator. 2 times 2 is 4. Okay, I did that one, so I got the hard part done for you. You do the numerator part. What would that be? Remember how to square a binomial? 2 ways. There's a little simple little formula, or you can FOIL it, whichever way you prefer. Which do you prefer? FOILing it. I was afraid you were going to say that. Okay, so this will be 1 minus cosine 2x times 1 minus cosine 2x. For some reason, my pen is so slow. Okay, when you do this, what does that give you? 1. Then the outer would be minus cosine 2x. Inners will be minus cosine 2x. And the last will be plus cosine squared of 2x. Okay. And then all you have to do is combine like terms, and that gives you 1 minus 2 cosine 2x plus cosine squared of 2x. Okay, that's a pretty ugly 2, isn't it? Okay, that's probably even uglier. Okay, let me see if I can erase it and make it better. Oh, man. I'm just so out of energy. Can't stand it. Okay. Now, that looks like we might have the answer, except we were to rewrite sine fourth x in terms of first powers of the cosine. There's a first power of the cosine, so there's a second power of the cosine. You need to deal with that cosine squared through x. And what in the world was a cosine squared? It's 1 plus cosine 2 times 2x, which would be 4x over 2. Okay, that's what the cosine squared 2x is. So let's take that and plug it into this. You have a 1 minus 2 cosine 2x plus a 1 plus cosine 4x over 2. All over 4. Okay? Well, that's a little awkward looking, isn't it? So what I'm going to do, there's several ways to go about doing it, but I'll do it probably the long, tedious way. That's 1 minus, it would be that tedious, okay. 1 minus 2 cosine 2x over 4 plus, get out of there, okay, 1 plus cosine 4x over 2 over 4. Okay? That's a little awkward, but that is the same thing, right? Now, how can we rewrite that over 1 denominator? You're dividing by 4, you're multiplying by 1/4. That just makes it a 1/8. So, this could be written as 1 minus 2 cosine 2x over 4 plus 1 plus cosine 4x over 8. So hard to write now. If you want the same denominators, just multiply this one by 2, but also multiply the numerator by 2. Okay, so let's see what that gives us. 2 minus 4 cosine 2x plus 1 plus cosine 4x. It'll show up one day. Okay, there it is. And then this is all over 8. Okay? Well, let's combine like terms. That would give us 3 minus 4 cosine 2x plus cosine 4x. Cosine didn't come out too well, did it? Over 8. I think that's it. Okay? Get out of there. Okay? Let's see if that's what they got in the book. Oh. Wait, where is it? Power reducing formula, that's where it is. And they factored out the 1/8 and called it, then had 3 minus, your numerator, 3 minus 4 cosine 2x plus cosine 4x. All over, yeah, times 1/8. Yes. That's what we got. Let's watch how they did it. See if they did it maybe a little bit easier, more straightforward, or did they just skip a bunch of steps? My guess is the latter, but let's just see. Note that repeated use of the power reducing formulas, sine fourth x is sine squared x squared. Exactly like we did. Okay? And because we already know what sine squared is 1 minus cosine 2x over 2, but that's squared, and when we square it, we get 1/4. Factor out 1/4. And then square that numerator, and you get 1. And here's the simple one, rather than foiling it, but that's simple too, is square the first, twice the product of the two, square the last. Okay, so that gives you that. Same thing as we got. They call it expanding it. Call it squaring the binomial. Okay. Now, everything is hunky-dory except they wanted this to first power. We have a second power there. So what they do next is write just like we did, that 1 plus cosine 4x over 2. They already have the 1/4 out front, so this might be a little bit easier to do. To get that all in the same denominator, we'll just double that over 2 and double this over 2. So it's 2 minus 4 cosine 2x plus that, all in the 1/4 out front. That makes it just a little bit easier. And when you do that, that's what you get. Oh, goodness gracious. They did everything at once here. Yeah, okay. 1/4 times 1 is 1/4. 1/4 times this would be 1/2 minus 1/2 cosine 2. And then they have a plus 1 over 2 times 1/4 is 1/8, and plus cosine 4x over 2, 1/4 is that. Okay. So this might be a little simple, I think it might be. Okay. Then they combine these two together, which gives them 2/8 plus 1/8 is 3/8. Okay. Minus 4/8. Right, 1/2. Plus 1/8. Okay. And when you do that, yeah, that's what you get. 3/8 minus. Well, they didn't do 4/8. They did left it as minus 1/2 plus that, and then when you pull out the 8, that changes it. So it would have made more sense to make this a 4/8 and then you pull out the 8. Either way you do it, you get the same answer. Okay, all to first powers. Multiple angles, but single power. Okay, that was example 4. And guess what? They have a good old checkpoint at the bottom, so you can give that a look too. Goodness gracious. They show using a graphing calculator, graphing first, y1 is sine fourth x, and then the graph is y2, what you just calculated to be 1/8 times 3 minus 4 cosine 2x plus cosine 4x, and then graph each of them, and you'll see the first one graphed and then the second graphed right on top of it. You watch it happen. And then there's a checkpoint. All right, well, goodness gracious, we found we can have double angle formulas, we can have power reducing formulas. Why can't we have half angle formulas? Okay? Yeah, okay. Well, here are, yeah, this shows, I'm sorry, I didn't know they had the slide here. You can use a graphing utility to check that result. Like I said, y1 would be sine fourth x, sine to the fourth x, y2 would be 1/8 of 3 plus 4 cosine 2x plus sine 4x, which is kind of interesting in one sense, okay? In that You know this is always positive. Sine x goes positive and negative. Sine squared is going to always be positive. Sine 4 is always going to be positive. So this is about how you would expect it to look, because it's always positive. What is a little surprising to me is that if you take 3 minus 4 times 2x, which would tend to make this fairly negative sometimes, and then plus 4 plus cosine 4x, and they don't look like they'd be all that positive, but this is at 3 always, and this sometimes is at 1. So 3 plus 1 would be 4. So yeah, you can see at least some of the time that's going to be close to 0, but this never outweighs this. This is plus that. Yeah. It just doesn't. So, but that's neither here nor there. All right, let's move to the half-angle formulas and how are we doing? Oh, good. We may get it done. Says you can derive some useful alternative forms for the power-reducing formulas by replacing u with u over 2. And these are called the half-angle formulas. So let's go back to those fun power-reducing formulas we just did. Here they are. Okay. Now I'm going to erase all my marks here, how we went about finding them. Now, this is a squared on this side with a double angle here. Okay? What we're going to do here is name this to be some single variable, what you want it to be. Rather than 2u, pick another variable. A. Okay, that'll be all right. So what we're going to do is let A equal 2u, right? That's legal in most states, right? Can you tell me what u is then? Is equal to what? A over 2. Okay. Get out of there. Okay. Now, let's plug that in here. Okay. Sine squared of u would then be sine squared of u is A over 2. Right? Is equal to, oh, let's do this too. Yeah, no, we're fine. We're fine. Is equal to 1 minus cosine of 2u. What is 2u? A over 2. Okay? And then all we have to do is take the square root of both sides. So this would produce sine of a half angle, A over 2, is equal to this plus or minus the square root of 1 minus cosine A over 2. There's a half angle formula for sine. Directly from here, just making a simple substitution. Oh, with one little problem, what in the world is plus or minus doing there? How do you know which one to use? See which quadrant it's in. Exactly. If A was in, like, the third quadrant we had last time, then A over 2 would probably be, was it what, third or fourth quadrant last time? Then it would be right over here. That would be in the second quadrant. Or it looks like it would be close to that. So then, sine in the second quadrant is positive. So you use the plus sign. Okay? Now we'll do the same thing down here with cosine. And what will that give us? We'll use the same substitution. Cosine squared of A over 2 is equal to, yeah, get back. Okay. A over 2, it's a pretty ugly A, is equal to 1 plus cosine of A over 2. And then take a square root of both sides of that, and you get cosine A over 2 is equal to plus or minus the square root of 1 plus cosine A over 2. All right, and again, that cosine in the fourth quadrant, A over 2 looks like it's probably be in the second. And if it is in the second, cosine is negative. In that case, you use the negative. Okay, so the plus or minus don't really hurt you that badly. Now, you could try to fiddle around with the cosine A's in the denominator and see what you did, or you could just do what we did before, divide by sine. Square A over 2, well, sine A over 2 and cosine A over 2. Now here's the part that they just kind of lose the plus or minus here, and they do it this way. Tangent of A over 2 would then be the square root of 1 minus cosine A over 1 plus cosine A. Okay? They lose the plus or minuses. The 2's, of course, cancel out when you divide. And that's what they get. Okay? Except they don't leave it like that. They didn't seem to mind radicals here, and they really aren't bad. But here you got a radical in the denominator. For some reason, it just didn't write well. I don't know what's going wrong with my pen. Okay, maybe I've thrown it around too much. So here's what we're going to do. Remember that little thing about a conjugate? Yes. Let's multiply by the conjugate of that denominator. 1, what would that be? 1 minus cosine A, wouldn't it? But if you multiply the denominator by that, you got to multiply the numerator by that as well. 1 minus cosine A. Okay? Well, the interesting thing you get here is, I'm going to write my tangent of A over 2 to then be equal to, I'll start with the square root, 1 minus cosine A times 1 minus cosine A, all under the radical here, is just, that's 1 minus cosine A squared. Square root of that is lose the square root. So there I wrote it, and I don't need it. Whoa! It won't erase either. Okay. So just write that as 1 minus cosine A over. But what do we have if we multiply 1 plus cosine A times 1 minus cosine A? Cosine squared A. And what in the world is that? Sine squared A, isn't it? Because they're actually identity. And that's a square, so you just have a sine in the denominator. 1 minus cosine A over sine A. Right? Nice. But what if we had chosen to, just because we could, multiply, for some reason my pen is not sure, okay, by the conjugate of the numerator instead. Okay? What would that give you for a tangent of A over 2? Well, why did it do that? Okay. All right. This then would be same as before. 1 minus cosine squared, which is sine squared. Square root of sine squared is sine. So you could write the sine up here. And then the denominator, where is my, okay, the denominator would be 1 plus cosine A. Because 1 plus cosine A times 1 plus cosine A is 1 plus cosine A squared. Square root of that is 1 plus cosine A. So here are the two different ways you can write this without radicals. The half angle form, sine and cosine, you've got to have a radical. And a plus or minus. But with the tangent, you don't need either one. Okay? And you have whichever form you prefer. And that, sure enough, is, let's go back to this. Where is it? Come on. Here you go. There we go. The sine of u over 2 rather than a over 2. It's fine. U over 2 is plus or minus the square root of 1 minus cosine u over 2, just like we got when we had a's. The cosine of u over 2 is plus or minus the square root of 1 plus cosine of u over 2. And the tangent of u over 2 is either 1 minus cosine u over sine u or 1 sine u over 1 plus cosine. And the signs of the SIG and signs of sine and cosine just depends on which quadrant u over 2 lives in. Okay, where it lies. Make sense? Okay. How are we doing? Oh! We've just run out of time. Okay. That was your half angle formula. Example 5 we didn't quite have time to do, so we'll start next time with example 5. Okay? And let me give you a few homework exercises. We came pretty close to finishing the section. Do any of the odds 7 through 13. They're all at calcchat.com, only 9's at calcview.com. Do any of the odds 15 through 19. They're all at calcchat. None of them are at calcview. Do either 21 or 23. They're both at calcchat, but 21's at calcview. Do any of the odds 27 to 33. They're all at calcchat. 27's at calcview. Do any of the odds 35 to 39. They're all at calcchat. 37's at calcview. Do either 41 or 43. They're both at calcchat. 41's at calcview. Do either 45 or 47. They're both at calcchat. 45's at calcview. Do either 49 or 51. They're both at calcchat, but 49's at calcview. Do either 53 or 55. They're both at calcchat. 53's at calcview. Do either 57 or 59. They're both at calcchat. Neither are at calcview. Do either 61 or 63. They're both at calcchat. 63's at calcview. Do any of the odds 65 to 69. They're all three at calcchat, but only 65's at calcview. Goodness, my throat's hurting. 71, you might find is an interesting problem, but it's the coolest picture in the world. But, hey, I mean, I just love that picture. I've seen it in several texts or versions of it. It just is incredible. But anyway, it's dealing with the Mach numbers, the number of times you're exceeding the speed of sound. It's an interesting problem. So you can either do 71 or 73, whichever you prefer. 75 is a true-false. It's fun to look at that and figure out why. 77 is then a complementary angle problem that you might find to be fun. The chapter summary is there on the next few pages, 390, 33, and 391. All the formulas and various identities in there, pretty much all of them are listed there. You might find a few that are not. Review exercises, they split these out by sections. You can do any of them you want. They're at calcchat. The odds are not at calcview at all, any of them. But there's 5.1, 2, 3, 4, and 5. So there's plenty of additional problems if you need them to look at. And there's a chapter test. And I think all the answers are in the back of the book, but calcchat only provides the workout solutions for the odd number exercises. And then there's a little thing on proof in mathematics, which is probably pretty fun to do. And there's a problem-solving postscript, or I guess that's what it stands for. I think it stands for problem solving, but they're using it for that. That means that next time we'll start on, well, we'll finish section 5.5, and then we'll get going on 6. But why was I telling you all about the things at the end of the chapter? Well, partly because I have your third test ready. And it's a weird looking 3 because I have changed. I used to do all 8 sections of chapter 2 as the second test. It's ever to get through all those, and students needed more grading. I felt like we would put it and then, well, chapter 6 that we just did, chapter 5 that we just did, then was chapter 2, it was test 2. Chapter 4 was just 1. So I just changed it on the key, on the master, so rather than typing it over. So you're wasting. Did I give you one? Yes. I did. You already took it away. She's anxious to get out of here, I can tell. Okay, you can get started on this. Don't expect to finish it this weekend by any means, because we haven't done all of them. So we'll do the last few that you'll see on there in class on Tuesday, and that gives you an extra weekend to work on it and ask questions or anything else next week. All right, good deal. We'll finish chapter 5, 5.5, and then we'll get started in chapter 6. And that'll take it to the end of the term, sadly, but true. Okay. Good deal. See ya. All right. I'm so confident, actually.